Students, can you able to see my screen?
Hello.
Hello. Whether my screen is visible to you? Students? This whether I am audible to you? Hello. Guys, please reply me whether my voice is audible and the screen is visible also. Hello. Anyone?
Sir, you are not audible. Your voice is not coming.
Okay. Hello.
No, you're audible.
Okay, fine. Okay, shall we start? Hello. Anyone? Students?
Yes, sir.
So, do you guys heard my voice when I presented the PPT?
No, sir.
No. Anyone able to see my PPT?
No, sir.
No. But my voice is audible.
Yes, sir.
Okay. Hello.
Yes,
Now,
sir.
what about
Yes.
now?
Fine,
Yes.
sir.
Okay. 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 So we can continue now. So actually, we have. I have given you an assignment about one problem. Have you tried to solve that problem? Anyone tried that problem? Okay, fine. No problem. We can solve that after finishing this topic. We can solve that problem. And what about that problems? Anyone tried the problems? What you have posted in the WhatsApp group and all? Whether you have tried that? Because one problem I have already taken one problem. I have solved one problem in our last class. But what about other problems and all? I think 4 problems you have posted in WhatsApp group. One I have solved, and the other 3 is there. In that 2 is not that topic we haven't covered yet, because that is about the centered expansion fans type, movable shocks and all. Okay, but the second problem is the same as the old problem what we have solved. Nobody solved.
No, sir.
Okay, fine. Okay, no problem. We can cover the topic and we can solve that 4 problems. Okay, sorry, 3 problems. What rest of the problems and all. So here now we are going to see about the 2 types of flows. This is also important because they will ask some questions like in a Rayleigh flow how the stagnation properties will change, or whether the entropy will increase or decrease. That type of questions will come from this Rayleigh flow and Fanno flow questions. Okay. Um, we are not going to derive the equations and all, but we will see some equations here, because no need of that deriving equations and all here, because it may take much time, but no need. We will see the clear concepts about this Rayleigh flows and all. Okay, so the flows inside some inside the combustion chamber and all, it will be like a constant area duct. Actually, Rayleigh flow is a flow which will be happen in a duct where there is no friction, but only there will be some heat transfer. There will be only heat transfer. So that type of flows are called Rayleigh flows. Okay, there's a Rayleigh flow is a flow which will be happening in a duct, and in the duct only heat transfer will be there, and we won't consider the friction force. The friction will be not considered here, it will be negligible. That type of flows is called Rayleigh flow. Okay, so for that purpose, here we are taking a constant area control volume. So for a constant area control volume, or we are taking a constant area duct, say it is a constant area duct, or else we can say it is a pipe. Inside a pipe the diameter is same. So in that part and all, we are selecting one small control volume, and certain equations will be needed for proceeding our the that means what and all properties will change. For that purpose we need to take certain equations. Okay, so first of all, here what we have is we are taking a control volume. Inside here, this is the region 1 in the control volume, and this is the region 2 in the control volume, and this is the selected area. So the flow will be passed from this region 1 to region 2. Between this region we will be adding or this control volume, or heat will be added to the control volume, or the heat will be rejected to the control volume from the control volume to the surrounding. Okay, so from the surrounding we will be adding heat, or from here it will be heat will be rejected. So the heat added or rejected, we are denoting that term as Q. Okay, and in region 1 the flow properties like thermodynamic properties like pressure will be P1, temperature will be T1, density is rho1, and the velocity is V1. In the same way, in region 2, after flow passing the control volume, the pressure will be P2, temperature will be T2, and density is rho2, and velocity is V2. Okay, so since it is a constant area duct, we know the mass flow, mass flow equations will come. So straight away, rho1 A1 V1 equal to rho 1, here we will get A1, and here it will be A2. Okay, so these two equations will come here. So we know it is a constant area duct, so A1 and A2 will get cancelled each other, so the remaining terms will be rho 1 V1 equal to rho 2 V2. Okay, and also we know that in this constant area duct there will be some mass flow, and also it will be at some velocity, so automatically momentum equation will be considered. Okay, so for momentum equation we know the equation is P1 plus rho 1 V1 square equal to P2 plus rho 2 V2 square. Then because we are adding some heat inside the control volume, then there will be some energy transfers. Okay, so therefore energy equation also we should be consider the energy equation also here. So for energy equation we know h plus v square equal to constant, h plus v square by 2 equal to constant. Okay, but here one more thing, we are adding heat, so the equation becomes for region 1 and region 2 they will be considering is h1 plus v1 square by 2 equal to h2 plus v2 square by 2. Okay, and we are adding heat to the system, so q will be come into picture, and also for h we are mentioning it as cp into t. So therefore the equation becomes q equal to cp into t2 minus t1 plus v square minus v2 square minus v1 square divided by 2. Okay, so mass equation, momentum equation, energy equation, why we are considering these three equations I have told you. Then one more thing, because of the heat is we are adding heat to the system, there will be temperature change, so that automatically because of the temperature change we will know, then the stagnation properties also will be considered. So from energy equations we know that q equal to h02 minus h01, that is equal to cp into t02 minus t01. Okay, so because energy equation we can write straight away here itself, we can write that is equal to h02 minus h01. Okay, since there is a temperature change, or we are adding heat to the heat gain, we know entropy will also change. With the heat gain there will be change in entropy also, so that s2 minus s1 equal to cp ln t2 by the t1 minus r ln p2 by p1. Okay, then we know the gas equation, we are considering gas only, so gas equation also will be, it is a perfect gas, we will be assuming it is a perfect gas, so that p equal to rho r t, so that p1 by rho 1 t1 equal to p2 by rho 2 t2. So these are the equations used for deriving the some certain parameters will be which will be changed after the flow past the constant area duct. Okay, so here we have we know what is Rayleigh flow and all. So there is a flow with in a constant area duct, which will be happened with no heat transfer. Okay, so here there is a line, this pink color line represents the Rayleigh line. It is drawn after the locus of points, all the points which is plotted after the successive completion of the process by heating or cooling from one stage to another stages. Okay, so the locus of all points which connects in the TS graph, this line is called the Rayleigh line. Okay, so here we can see, we all know that in the previous slide also I have explained, because of the heat gain is there, then there will be a entropy change also. So that's why we are plotting the graph between T and S. Okay, so here in the graph we have three regions. This is one region, this is second region, and this is the third region in the graph. Okay, I'm just differentiating the graph, that's why, but there is no type of regions down, because we are considering only constant area duct. We can draw like this. So here we have a constant area duct, and the flow will be passed inside this constant area duct. This is a duct, we can just assume that this is a duct, so that flow, this will be the inlet and this will be the outlet. Okay, So first of all, what I am doing is I am just passing a subsonic flow inside the duct, and I am just adding heat to this subsonic flow. Okay. Suppose subsonic flow is flowing inside the constant area duct. According to Rayleigh flow, when we are applying heat to the system, this is the system. This is the system. So in the system, because of the heat, what will happen means the Mach number will be increased. For subsonic flow, if you are if you are adding heat to the gas which is flowing inside the constant area duct, automatically the Mach number will be increased, and it will increase up to this B point. Okay. So by adding heat, we can straight away say temperature is increased, and also this entropy is increased. Entropy is marked here, so that it will be increased up to here. Okay. Then if a supersonic flow is passed inside the duct, first of all my condition is a subsonic flow is passed. While passing a subsonic flow and adding, when we are adding heat, automatically the velocity of the flow gas will get increased. Okay, up to Mach equal to m equal to 1. And if you are adding if you are passing supersonic flow, and when we are adding heat to that gas in a supersonic, when we are passing supersonic flow, and if you are adding heat to that, means automatically the velocity will get decreased. So for subsonic flow, by adding heat, the velocity will be increased, but for supersonic flow, the velocity will be decreased, and it will be decreased, and it will be the Mach number will be
What?
decreased. Okay. Yes.
Sir, how it decreases for supersonic flow? Could you please explain this concept elaborately, sir? I couldn't get this.
Actually, see, we know for a supersonic flow, when we are cooling the gases and all, normally if you are we can just say like this: what is expansion process? When we all know, we have come across the expansion waves and all. Okay. So in expansion waves, there is an isentropic process. Expansion waves comes from isentropic process only. Okay. So because the shocks and all, we will be that is a adiabatic flow. And for expansion waves and all, it will come from uh, what to say, expansion waves means the isentropic process will come. Okay. We all know, when we are cooling the gas, it will become expansion. That means the heat will be reduced, so that it will be like an expansion phase. So automatically the temperature is decreased. The temperature decreased means automatically the pressure is also decreased, so that the velocity will get increased. Okay. That's the thing happening for supersonic flows. This is the conditions. This is how will happen. That's what Rayleigh tells. Okay. Based upon his theory, when we are adding heat to the flows, means in subsonic flow, the Mach number will get increased, but for supersonic flow, automatically the Mach number will be reduced, because since the concepts and all, we have already crossed the pressure ratio. When we are decreasing the pressure ratios, automatically the velocity will get increased. Okay. That's the thing happening. Okay. So these things and all, for another one condition is, first we are adding heat to the pipe. Secondly, when we are cooling the gas in subsonic flow, when we are cooling the gas, the Mach number will decrease. That means the flow will get the velocity of the flow get reduced. But for supersonic flow, when we are cooling the gas, automatically the flow will get increased. That means the Mach number gets increased. Okay. Okay. You can see here some temperature changes across the flows. That means upon heating, for subsonic flow, the temperature after the gas, here it is greater than 1. T02 is greater than T1. And also here you can see here, for subsonic flow, the velocity, upon heating, the velocity is increased. Mach number is velocity increased means automatically Mach number is increased. The stagnation properties also, upon heating, it will get increased. and the density is decreased, stagnation pressure decreases, and the entropy when we are increasing, it will get increased. Okay, then after that here up to B point it will get increased, and the Mach number at this point it will be, the formula is ma equal to 1 by root of k. This k is nothing but gamma, that is 1.4, gamma equal to 1.4. So the Mach number at this point will be ma equal to 1 by gamma. Okay, 1 by root of gamma. This is the conditions what we need to remember, and for cooling this may happens. Just note this properties. This is important for you. For Rayleigh flow, they may ask this type of questions only. Okay. And note this also. Okay. These two conditions, because questions will come from this type of conditions only. And one more condition, in Rayleigh flow we won't mention the duct length and all. Okay, but in Fanno flow we will be mentioning the duct length, because we are increasing the duct length only. Okay. Finished? So also listen, in subsonic flow, because of the entropy also the Mach number is increased. Okay. So in subsonic flow, by heating the entropy increases, and by cooling the entropy decreases. Okay. So that's why in subsonic flow and all, by adding heat the Mach number increases, and also by um, cooling the system the Mach number decreases. But for supersonic flow, by cooling we will get the uh, flow get in Mach number get increased from unity to, that means the choked condition, to the supersonic speed. Okay. Finish. Shall I change the slide? Hello guys, students? Students, can you able to hear me?
Yes, sir, you're audible.
Yes. Whether you have finished?
Yes, sir.
Okay, fine. So the fundamental equation to for a Rayleigh flow is P plus G square V equal to constant. Okay. P plus G square V equal to constant. And these are the equations which denote the properties across the waves. Okay. So P2 by P1 equal to this. Here the K is gamma. So in this book what I have referred, it is a K, that's why I have put it K like this, but you just put it as gamma. Okay. So P2 by P1 equal to 1 plus gamma m a1 square divided by 1 plus gamma m a2 square, or you can just say m1 square and m2 square. Okay. Same way, T2 by T1 equal to m a2 divided by, like this. Just write all these formulas. These are the properties change, how the thermodynamic properties will change when we come across this Rayleigh flow. Okay. just write this. After that we can solve one problem also regarding this, so that it will be clear how the properties are changing, how why it is changing and all. You can get a clear idea of that. For all k, just put gamma. Okay, k is gamma, and don't confuse. Or if you are putting k also, just note that k equal to gamma, then it will be easy for you. Don't worry for I think if you are not understood, I will show you some examples how the heat is increasing when we are adding heat to the subsonic flow and all. Okay, so that it may helpful for you. Once finished, please tell me.
Please go ahead.
Finished? Okay, fine. So last condition is the choked flow. There is a choked flow is we know in a supersonic flow and in subsonic flow, while heating the Mach number decreases, that is the velocity decreases up to Mach m equal to 1 only. Okay, after that it is not decreased. So in choked Rayleigh flow, the fluid will be at critical state when the Mach number is will be equal to 1. So when it will occur means when the maximum heat is added to the session or added to the system, the supersonic flow will be decelerated, and the Mach number will be reduced to 1, and after the choked condition there won't be any mass flow rate inside this duct flow. Okay, so at this condition we'll be having the Q max equal to H naught star minus H naught 1, that is equal to Cp into T naught star minus T naught 1. Okay, so this for gamma equal to 1, the value of this T naught by T naught star equal to 0.49. So and we can see here, therefore if the critical stagnation temperature is 1000 Kelvin, so the stagnation temperature critical at the critical state is 1000 Kelvin, the air cannot be cooled below 490 Kelvin in Rayleigh flow. Okay, so it cannot be cooled below 490 Kelvin in Rayleigh flow. That means we all know when after the choke condition there won't be any mass flow rate inside the nozzle also, then the flow will be choked. So that we can easily say when if it is cooled below 490 Kelvin, automatically the Mach number will be reached m equal to 1, and after that if it is if you are continuing that, there won't be the Mach number cannot be supersonic, so that the flow undergoes a normal shock wave, and after that it will become subsonic only. Okay, so that see here the limits for this T by T naught star equal to 1 by 1 minus 1 by k square, not gamma square. So just note this formula also. Okay, okay. So next is the Fanno flow. So before going to this, we can try to solve one small problem. Okay, so actually this Rayleigh flow and Fanno flow is little bit complicated only, because in Rayleigh flow we will be considering the heat transfer, that means heat addition or rejection. In Fanno flow we will be considering the friction, that means In Rayleigh flow, we'll be only adding the heat. For Fanno flow, what we will do means because of the friction only the flow will be decreased or increased. So that we will be for providing friction, we need some extra surface. So we will be extending the length of the duct to make the flow supersonic or to make the flow subsonic. Okay, that's why we will be seeing. So first we will have a small idea about how to solve this sum regarding this Rayleigh flow. Okay, so I can dictate a problem. So air enters a constant area duct. Air enters a constant area duct at m1 equal to 0.3. Okay, and pressure will be P1 equal to 1 atmospheric, 1 atm. Okay, and the temperature is T1 equal to 300 Kelvin, and the heat added per unit mass is Q equal to 3 into 10 raised to 5 joule per kg. Heat added is 10 raised to 5, sorry, 10 raised to 5 joule per kg. Okay, so what we need to do is we need to calculate the flow properties. The flow properties, what we need to find is T2, P2, M2, rho 2, then T02, P02. Okay, these things we need to find. This type of problems they won't ask, but still we can solve one problem. So these are the given data. So they haven't mentioned about the gamma value, so that we can just take the gamma value. Okay, so they have given like air enters a constant area duct, and they haven't mentioned anything about the friction and all, so we can straight away consider. And also they have given heat transfer here, so we can straight away take this is a Rayleigh flow. Okay, so first what we can do is we know some certain formulas what we have. That is P2 by P1 we have a formula, then P star by P we have some formula, T2 by T1 we have some formula. Okay, and T by T star also, that means so these things are some formulas we have here. Okay, so based upon these things we can find, because if we know P1 we can find P2, if you know T1 we can find T2, if you know rho 1, sorry, and know the value for this MA1 MA2 and all, we can easily find P2, because they have given the value for P1, they have given T1, they have given rho 1 also. Rho 1 I think didn't mention, I think so, only T1, P1 and M1 given. We can find rho 1 also. So remaining things we need to find MA1 MA2. Okay, after finding the MA1 and MA2 we can easily identify which type of flow it is, and what is the pressure behind that. Okay, so initially they have given one factor like m equal to, sorry, m equal to 0.3, not m equal to 3. Okay, m equal to 3, this is not 0.3, just write m equal to 3. Okay, so everyone know about this isentropic tables and all. Have you heard about isentropic tables? See, for solving oblique shock, normal shock, isentropic relations and all, and also for Rayleigh Fanno flow and all, we have specific tables like gas table. So in this gas table, just if certain parameters like this type of parameters given, we need to take values like from the isentropic table. For m equal to 3, there will be some properties like T1 by T01, or T naught by T there will be. Okay, so here T1 by T naught 1, we need to take the values for T1 by T naught 1 and also P by P naught, P1 by P naught 1. Okay, so the values from for this Mach number, the values are for T1 by T naught 1, that is 0.357, 0.357. Okay, and also for P1 by P naught 1, 0.0272. Okay, 0272. So with this formula we can find the value for T1, T naught 1 and also P naught 1, right? Because from this formula we know the value for T1 and we know the value for P1 also. By substituting the value and the cross multiplication, we can just find the value for T1 and T naught 1 and also P naught 1. Anyone please find the value for this T naught 1 and P naught 1? And also for your for this Rayleigh flow example, how heat is added, how the velocity is increased for subsonic flow, means we can easily visualize that example from your pressure cookers and all. Okay, in your pressure cooker, do you guys noted the pressure cooker? Have you seen the operations of this pressure cooker in your home? Students, hello, students, are you there? Hello, anyone, guys? Hello, students. Students, can you able to hear me? Hello, anyone? Chandan Singh, students. Hello, anyone? Yes, please reply me. Guys, are you there? Hello, students.